good day. Welcome to our video lecture series on separation processes, more specifically binary distillation using the Mercantile method. In this video, we'll be continuing the material imbalances. However, more specifically, we'll be identifying material balances for the rectifying section and also for the stripping section. Later on in this video or in another video, we will be discussing the Q line and how it plays an integral role in developing the Mercantile diagram. However, before we get into the material balance itself, we must first understand the flow rates within the rectifying section. Now we have a flow rate of Vn+1 going up the column. It is coming from the n+1 stage because this is the n stage. Therefore, in this column we are counting top to bottom. Therefore, the vapor will be coming from the n+1 stage. Similarly, the liquid is flowing down the column. Therefore, it's flowing down from the end stage, so we have a liquid flow rate of Ln. Now, in the majority of the cases, we assume that the concept of constant molar overflow applies. Now, the concept of constant molar overflow is the assumption that is made, which states that the vapor and the liquid within the rectifying section of the column, their flow rates are constant. Therefore, the vapor that is coming from the n+1 stage has the same flow rate of the vapor leaving the end stage, and it also have the same flow rate of the vapor leaving the second stage, and the same flow rate of the vapor leaving the first stage and going to the condenser. Similarly, the liquid leaving the first stage would have the same flow rate of the liquid leaving the second stage, and that will also have the same flow rate of the liquid leaving stage n, which is Ln. So understanding and applying the concept of constant molar flow is essential for building these material balances. So now we will develop the material balance for this system, utilizing again the equation input is equal to output that we developed in the earlier videos, and we can now set our system boundary, which is cutting through the top half of the column, the rectifying section, and also including the condenser and cutting the distillate leaving the column. And this is our system boundary that we will be utilizing to form our material balance. As usual, we will start with our total balance. So as I said previously, our total balance input is equal to output. Vn is the only input going into the system boundary, and the outputs would be D and Ln, which is seen here, D and Ln. Assuming that constant molar overflow applies, the Vn could be written as now V is equal to L plus D, and this can be used in the further equation. So now we can write a material balance for the most volatile component. So as you can see, we develop the material balance for the most volatile component. Vn+1 multiplied by Yn+1, which is the mole fraction of the most volatile component, that is the input, is equal to the output, which is Ln multiplied by Xn, which is seen here, bring out the stage, plus D by Zd, which is the flow rate leaving in the distillate on the overhead product. Now, utilizing this equation, we can now make Y the subject of the formula. So when we make Y the subject of the formula, we get this equation here. Y is equal to L divided by V multiplied by X plus D divided by V multiplied by ZD. Now this equation is the equation for the upper operating line in the Mercantile method, or the rectifying line in the Mercantile diagram. And I will highlight what that specific line is further in other videos or further in this video. But now what we would want to do is substitute for V, because from the total balance we know that V is equal to L plus D. We want to substitute that into the equation. Once substituting for the value of V, we will get this new equation, Y, which is equal to L divided by L plus D multiplied by X plus D divided by L plus D multiplied by ZD. So what we like to do in this step is to divide the numerator and the denominator in the left hand side of the equation. For the individual terms, we divide the numerator and the denominator by D, the distillate. Now, once we do this, we will get this equation, which is highlighted here, which could be further simplified. Now, in previous videos, we defined the reflux ratio, or the reflux for the column, which is denoted by the letter R, is equal to the liquid LO flowing back into the column. However, due to the fact that we assume that the concept of constant molar overflow applies, this term LO would also be equal to L. So we can write this as L, and the reflux ratio, as I said, is the ratio of the liquid flowing back into the column to the distillate leaving. So R, the reflux ratio, is equal to L over D. And we can now substitute it into this equation here and further simplify it to show the following. Once we substitute the value of R and we simplify the equation, we are able to get this equation, which is the equation that most of the time you would use in the Mercantile method. Now this equation can be separated to resemble the equation for a straight line. And the equation for a straight line is Y is equal to M, which is the gradient, X plus C. So we could utilize these values to construct our upper operating line, or our rectifying operating line. Now the rectifying operating line is the line that highlights the upper section of the column. Now we have our graph here, and we have our Y is equal to X line, our 45-degree line. And let's say we have an equilibrium curve as shown in the diagram that I'm drawing. We first go by the point ZD. We draw a vertical line upward to the Y is equal to X line, which is the 45-degree line. Now we can first construct our upper operating line. Now we start at this point on the Y is equal to X line, and we can draw our straight upper operating line, and it should look something like this. Now the gradient of this line is shown here as R divided by R plus 1, and our Y intercept value, that where the upper operating line cuts the y-axis, is shown here in this term, which is equal to ZD divided by R plus, oh sorry, this should be 1, this isn't Y. So the y-intercept here, because D divided by D is equal to 1, so it should be ZD divided by R plus 1, and that is our y-intercept term for the operating line. Before I conclude, in order to draw this upper operating line or this rectifying line, you must have either 2 points on the upper operating line, either here or here or even here. At least 2. You need at least 2 to draw the line, or you need one of the points and the gradient, which is the gradient of the line is equal to r divided by r plus 1. Or you could have one of the points and also the y-intercept, which is equal to zd divided by r plus 1. Now once we have our reflux ratio and our value for the most volatile component in the distillate, we can substitute it into the equation and either get the gradient or the y-intercept to draw this rectifying operating line.